Graphical intuition of increasing and decreasing functions. Welcome, everyone. In this subsection, we are going to develop a visual understanding of how functions behave. Now, before we dive into more complex formulas and the concept of derivatives, it is essential that we first establish a clear intuition of what it actually means for a function to increase or decrease, simply by observing its graph. Once we have this visual foundation, it will be much easier to apply the mathematical rules and examples that we will cover in the following slides. The fundamental rule of reading graphs. Now that we have an overview of our goals, let's establish the most important ground rule for this topic. In mathematics, whenever we analyze the behavior of a function, f of x, we always observe the graph from left to right. To be more specific, this means we are tracking what happens to the height of the graph, which is represented by the y value, as the input, or the x value, increases. By keeping our movement consistent from left to right, we create a standard way to determine if the function is climbing or falling, which will allow us to formally define increasing and decreasing functions in the next few slides. Visualizing an increasing function. Now that we have established the fundamental rule of reading graphs from left to right, let us apply that logic to understand what an increasing function looks like. First, I want you to imagine that you are physically walking along the curve of a graph, starting from the left side and moving toward the right. As you move, pay attention to your elevation. If you find yourself climbing upward, as if you are walking up a hill, the function is said to be increasing. To describe this more formally in mathematical terms, a function is increasing if, as the x-coordinate increases, the corresponding y-coordinate, which we also refer to as f of x, also increases. In other words, as you move forward along the x-axis, the height of the graph rises. In simpler terms, if the graph moves upward as you move to the right, you are dealing with an increasing function. Keep this visual image in mind, as we will now look at the opposite behavior in the next slide. Visualizing a decreasing function. Now, let us look at the opposite scenario. Just as we previously discussed with increasing functions, imagine you are walking along the curve of the graph from left to right. If you find yourself moving downward, the function is said to be decreasing. To put this in more formal mathematical terms, a function is decreasing if, as the x-coordinate increases, the corresponding y-coordinate, which we also refer to as f of x, decreases. In simpler terms, if you observe the graph moving downward as you move your eyes to the right, you are looking at a decreasing function. Detailed example, the parabola fx x2. Now that we have established the theoretical basis for increasing and decreasing functions, let us apply these concepts to a practical example. We will use the well-known quadratic function, f of x equals x squared. As you may recall from your previous studies, the graph of this specific function is a parabola, and its lowest point, known as the vertex, is located exactly at the origin, which is the point 0, 0. Step-by-step analysis, left side of the y-axis. Now, let's put our theory into practice, using the parabola we just introduced. First, let's focus our attention on the left side of the y-axis, which is the region where x is less than 0. To see exactly how the function behaves in this area, let's pick two specific points to compare. For instance, we can choose x equals -3 and x equals -1. If we plug -3 into our function, we calculate -3 squared, which gives us a height of 9. Similarly, if we look at our second point, -1 squared equals 1. So, the height at this point is 1. Now, remember the fundamental rule we discussed earlier. We always read the graph from left to right. As we move from x equals -3 toward x equals -1, we can see that the height of the graph drops from 9 down to 1. Because the height is dropping as we move to the right, we can conclude that for all values where x is less than 0, the function is decreasing. Step-by-step analysis, right side of the y-axis. Now, let us shift our focus to the right side of the y-axis, specifically the region where x is greater than 0. To analyze the behavior of the function in this area, let us select two sample points. For example, x equals 1 and x equals 3. First, let us determine the height of the graph at x equals 1. By substituting this value into our function, f of 1 equals 1 squared, which gives us a height of 1. Next, let us look at the point where x equals 3. In this case, f of 3 equals 3 squared, which results in a height of 9. Now, applying the fundamental rule we discussed earlier, always reading the graph from left to right, we observe that as we move from x equals 1 to x equals 3, the height of the graph rises from 1 up to 9. Therefore, since the y value increases as the x value increases, we can conclude that for all values where x is greater than 0, the function is increasing. Step-by-step analysis, identify the turning point. Now, having analyzed both the left and right sides of our parabola, let us look at the point where these two behaviors meet. At x equals 0, the graph stops decreasing and begins increasing. This transition marks a critical change in the function's direction. Consequently, since this is the lowest value the function reaches before it turns back upward, we identify this point as the minimum of the function. Real-world analogy, the roller coaster. Now that we have analyzed the mathematical behavior of the parabola, let us use a real-world analogy to solidify this intuition before we wrap up the lesson. Imagine you are riding on a roller coaster track. First, consider the moments when the coaster is climbing a hill. As the coaster moves forward, which is equivalent to our x value increasing, the altitude, or the height, is increasing. This is a perfect physical representation of an increasing function. Conversely, think about when the coaster is plunging down a steep drop. Again, as the coaster continues to move forward, the altitude is decreasing. This represents a decreasing function, much like the left side of the parabola we just studied. Finally, imagine if the coaster moves along a completely flat platform. In this case, the altitude remains the same even as the coaster moves forward. This represents what we call a constant function. By keeping this roller coaster imagery in mind, you can easily visualize whether a function is increasing, decreasing, or constant simply by imagining the ride of the graph from left to right. Key takeaways. Now, let us consolidate everything we have discussed so far with these key takeaways. First, regarding the direction of analysis, always remember the fundamental rule we established at the beginning: you must read the graph from left to right. This ensures that we are observing the behavior of the function as the x value increases. Next, let's recap the visual cues. A function is increasing when the graph moves upward. In other words, as the x value increases, the function's value, or f of x, also increases. Conversely, a function is decreasing when the graph moves downward. This means that as the x value increases, the function's value, or f of x, decreases. To illustrate this with the example we analyzed earlier, consider the function f of x equals x squared. As we observed in our step-by-step breakdown, this function is decreasing on the interval from negative infinity to 0, and it is increasing on the interval from 0 to positive infinity. Now that we have a firm grasp of these concepts, let us move on to the final slide to discuss some common mistakes you should avoid to ensure your analysis is always accurate. Common mistakes to avoid. Now that we have covered the core concepts and the roller coaster analogy, let us conclude by discussing some common pitfalls to avoid to ensure your analysis is accurate. First, be careful not to read the graph from right to left. As we established in our fundamental rule at the beginning of this lesson, we must always observe the graph moving from left to right. If you accidentally read it backwards, you will perceive an increasing function as a decreasing one, leading to an incorrect conclusion. Always ensure you are moving in the direction of the positive x-axis. Secondly, it is important not to confuse the input, x, with the output, which is f of x or y when we use the terms increasing or decreasing. We are referring specifically to the behavior of the output. In these analyses, we always assume that x is increasing as we move to the right. Our primary focus is to observe how the y value responds to that change in x. Finally, avoid the mistake of ignoring the interval. As we saw in our step-by-step analysis of the parabola, a function is rarely increasing or decreasing across its entire domain. Therefore, you should always specify the exact interval where the behavior occurs. For instance, rather than saying a function is simply increasing, you should be precise and state that it is increasing for x greater than 0, as this provides a complete and mathematically accurate description.